In this video, I would like to show my milestone 2. And let's run the program first. Okay, and the scheme works and looks fine. And now I want to show my codes. First of all, I want to show where is the well, inverse matrix of the Born pose. Here in the cluster, every time we find a transform matrix and a transform link matrix, we get the link dot inverse times transform, and then this is the matrix. And then we just copy all the rows to our math engine matrix. So just create 4 vectors and copy the vector to the matrix. And this is the verification. Okay, the transforms and the this is probably the transform links, and then this the created matrix. And then the second part is the weight and indices. Okay, the same thing here. Weight and indices are here. These the indices and these are the weights. And just follow everything in the lecture and created a table called weight and index table. It should at the end. Okay, and for each vertex, we have the Born number and the weight. And okay, and for the Born number, we have to know this is the real number of the Born hierarchy in the beginning. So I just give the every hierarchy an index, and so we can look for the different Born names with different indexes. And next one is the vertices. Vertices, because we have done it in game 575, but the problem is when we do that, we sorted it with the XYZ. However, we cannot make sure that that order is the same as the Born. That number is not the same as this vertex number. So I just try to find which one should be the exact vertex number. So let's see here. Here, this number here is the actual index number. So I just create a new field called index in the output vertex NST, and you can see this structure here. Here. Okay, this is the old one, but the new one, I add an index. So now when we sort it, we just base on the index. So equal is just the two indexes are equal, and less than just we just compare the two indexes. That's that can make sure all the words have all the Born weights and the vertexes are the same one. But now we have to copy this structure to this one. So and we can output this the old structure. They're the same thing. And also for the Born word matrix. Okay, the Born word matrix. When we, in the animation part, we get the different Born locals at time t, and I'll show here. Okay, this one we have different frames and the list of Borns, but at time t, we calculated the Born results, which save the TQS, transform quaternion and the scale in the Born at T. And in the game object animation, we change the TQS to a real local matrix. And then we loop from the animation game objects to get the word matrix of each Born. So I just copied that word matrix to the Born word matrix here and use this Born word matrix to pass it to the GPU. And in the future, in the milestone 3, I will save these Born locals to different parts, and this is my plan how to save it. And then we just multiple all the identity index matrix and just multiple everything and get the Born word and then pass it to GPU. Okay, and okay, here we have a problem here. Okay, when we got the Born local matrix, we don't know we don't know which one is calculated first because they are put in a PCS tree, and we don't know the real implementation of the PCS tree. So we have to have a method to find which one correspond to which local in the two matrix arrays. So now I create a hierarchy table, and I can show it here. Okay, here just hierarchy table, the heaps and the parent. Okay, the child and the parent, and also we have the depth. This one is used for the magic table. Okay, and in the animation part, okay, here we just want instead of just putting everything in the game object hierarchy, we have to know the max depth. If the max depth is and save it to the columns, and the rows are the Born numbers of the and so we can set up the magic table. Okay, but this part we didn't do that. This part we did the setup Born word. For each Born word, because we have known the game object Born word, so we just copy it to the table. Yeah, and first we have to allocate a pointer and then pass it to the GPU. Okay, and for scheme part, okay, and for the constructor of the scheme model, we create a VAO. When we create a VAO, we just get the VBO 0 and 1, which is worth and tries. And also we created a new VBO called VBO 2, which saves the weights and indexes. And also we load VBO 1 and VBO 2. Load VBO 0, the same thing as the old one. Just load the words and different layouts. And the VBO 1 data is very simple here, and the VBO 2 data looks like very similar to the VBO 0. So that's it. And the graphic object, yeah, we just want to pass the aim matrix and the Born word to the GPU. Also for the scheme game object, this one is quite simple because we don't want to use the p word, because this one is a list of bone words. For example, in the humanoid is 80, so we don't want to use the old one in the game object. This one is just one word, so we create a new we create a new matrix pointer and pass that to the GPU. And here we just set up private update. We set up the bone word, and here set up this bone word, and then pass it to graphic objects. And also here we have no memory leaks, and this one just for the verification. And that's it.